Jai Hind everyone. I am Jyoti Sharma giving you a lecture series on the topic transformer, which is from unit 3 of basic electrical engineering. It's a course in first year according to AKTU and the subject code is KW101. In the previous 4 lectures we have seen the working of the transformer, the ideal transformer and the practical transformer on no load conditions, their equivalent circuits, their phasor diagrams, the efficiency, voltage regulation of transformer. Now coming to certain more topics on transformers. So this is lecture 5, it will be having the contents like auto transformer, 3-phase transformer connections, classifications of magnetic materials and the explanation for BH curve, or we also used to know it by hysteresis curve or hysteresis loop. Coming to auto transformer, an auto transformer is a type of electrical transformer with only one winding, right. So the auto, that prefix that refers to the single coil acting alone. In the Greek, this auto means self, not to any automatic mechanism. An auto transformer is similar to a 2-winding transformer, but varies in the way the primary and the secondary windings of the transformer are interrelated, right. Now in an auto transformer, one single winding is used as the primary winding as well as the secondary winding. It can be seen in the figure, the same winding, what it can be seen over here, the portion of it is working as primary and a small portion of it, what we call it as BC, that is serving the purpose for secondary. But in the 2 windings transformer, the 2 different windings are being used for primary and the secondary, right. So it can be seen from the very much this diagram, that is the diagram being showing an auto transformer. In fact, once again the same function step up or step down can be performed, and this is a step down auto transformer, right. So the winding AB of the total turns N1 is considered as the primary winding, whereas this winding is tapped from the point C and the portion BC is considered as secondary, right. If at all we just assume that the number of turns in between the points B and C is N2 and between A and C the total number of turns is say N1. V1 is the applied voltage across the primary winding, that means between the across the total winding, that is A and C, between the points A and C. So the voltage per turn in this winding would be given by V1 by N1. So the total voltage which is occurring across the portion BC of the winding, that has to be now given by V1 upon N1 into N2, and from the given figure what we have seen in the earlier case, this voltage is what we are calling it as V2. We are calling this voltage as V2. Right. So now this V1 upon N1 into N2, that will be given by V2, or if it is take the ratio, then once again V2 by V1 or N2 by N1 is going to be the constant K, what we call this K as the transformation ratio, given by the secondary terminal voltage by primary voltage or secondary number of turns by primary turns. As BC portion of the winding is considered as secondary, it can be easily be understood that the value of the constant K is nothing but the turns ratio or the voltage ratio or the transformation ratio of that auto transformer. When the load is connected between the secondary terminals, that means between B and C, then obviously the load current I2 used to start flowing that. The current in the secondary winding or the common winding is the difference of I2 and I1 of S. Now, the very important advantage of using an auto transformer is, as instead of 2 windings we are using just single, so obviously we are saving the copper in it, right. So we are going to derive how much copper we are saving in an auto transformer compared to a 2-winding transformer. Now as we know that the weight of the winding of the copper, right, that depends upon its length and the cross sectional area, right. Again the length of the conductor in the winding is proportional to the number of turns, and the cross sectional area that varies according to the current, right. So the weight of copper in a winding is directly proportional to the number of turns and the current, the rated current of that particular winding. Therefore the weight of the copper in the section AC, that is proportional to, if at all I am considering the same figure what we have seen in case of the step down auto transformer, right? In that case AC is the total number of turns, right? That is the total primary which is occurring. So in that case, so the weight of the copper in that section is just proportional to N1 minus N2 into I1. Similarly, the weight of the copper in the section BC, here the number of turns, how much is the number of turns over there? So the number of turns over there was just N2, and the current which is there, that is I2 minus I1, right? So the total weight of copper in the winding of the auto transformer, that is proportional to N1 minus N2 into I1 plus N2 into I2 minus I1, the addition of both of them, right? Just solving that, resolving these two, N1 I1 minus N2 I1 plus N2 I2 minus N2 I1, the final expression I am getting is 2 times of N1 I1 minus N2 I1, okay. Now similarly I have to compare it with the 2 winding transformer, right? So for a 2 winding transformer, the weight of the copper that can be given, that must be proportional to, we just see that the weight of the copper is proportional to number of turns and the current. So in the primary winding, the number of turns is N1, current is I1, number of turns in the secondary is N2, current is I2, so the addition of these two will give me. Now since in a transformer N1 I1, the MMF, that is going to be same, so I may just write it as twice of N1 I1, right? Now going for, say let's assume that WA and WTW are the weight of the copper in auto transformer. This is the weight of copper in auto transformer, and this is the weight of the copper in 2 winding transformer. Then in that case, if I take the ratio of the weight of copper in auto transformer to the weight of copper in 2 winding transformer, it has to be the ratio twice of N1 I1 minus N2 I1 upon twice of N1 I1, right? Resolving it, what I used to have, that the weight of copper in auto transformer is 1 minus K times the weight of copper in 2 winding transformer, right? If that's the case, so how much is the copper being saved compared to a 2 winding transformer? So in that case, I have to go, the copper saved or the saving of the copper in auto transformer, that will be given by the weight of copper in 2 winding transformer minus the weight of copper in auto transformer. So if at all I just substitute WA as the weight of copper in 2 winding multiplied by 1 minus K times, I will be getting K times the weight of copper in 2 winding transformer. Similar is the case when this is for a step down auto transformer, right? If at all I go the same derivation I do for a step up auto transformer, in that case I will be getting this as 1 upon K times the saving of the copper, that will be the 1 upon K times the weight of copper in 2 winding transformer, just the reciprocal of the transformation ratio. So let's see what are the advantages of using this auto transformer. So the advantages, that includes the very first one, for transformation ratio say 2, right? So the size of the auto transformer would be approximately 50% of the corresponding size of the 2 winding transformer, that means the size would be smaller. For the transformation ratio say 20, however the size would be 95%, the saving in the cost of the material is of course not in the same proportion. The saving of the cost is appreciable when the ratio of the transformer is lower than 2. Thus the auto transformer is smaller in size and cheaper also, right? An auto transformer has higher efficiency than the 2 winding transformer, right? This is because it is having a less ohmic loss and the core loss due to the reduction of the transformer material, right? Also the auto transformer has better voltage regulation, as the voltage drop which is occurring in the resistance and the reactance of the single winding is less, okay. Now what are the disadvantages by using auto transformer? The very first disadvantage is because of the electrical conductivity of the primary and secondary winding, the lower voltage circuit is liable to be impressed upon by higher voltage. To avoid breakdown in the lower voltage circuit, it becomes necessary to design the low voltage circuit to withstand higher voltage. Second is, the leakage flux between the primary and the secondary winding is small and hence the impedance is low. So what it will result in? It will result in the severe short circuit currents under faulty conditions. The third point, The connections on the primary side and the secondary sides have necessarily needs to be the same, except when using the interconnected starting connections. This introduces complications due to the changing primary and the secondary phase angle, particularly in the case of delta-delta connections, right? Because of the common neutral in the star-star connected auto transformer, it is not possible to earth the neutral of one side only. Both their sides should have their neutrally either earthed or isolated, right? If we just see the third point and the fourth point, these are being related with the three-phase auto transformers, right? Fifth point, now it is more difficult to maintain the electromagnetic balance of the winding when the voltage adjustment tappings are provided. So it should be known that the provision of tapping on an auto transformer increases considerably the frame size of the transformer. So if the range of the tapping is very large, so the advantage gained in the initial cost, right, is lost to a great event or extent. Going for the applications, right, what are the applications of auto transformer? Now it can be used as a compensating voltage drops by boosting the supply voltage in the distribution systems, right. Auto transformers with the number of tappings are used for starting induction synchronous motors, right. As the AC motors, they require the starting methods in the sense as the initial resistance and reactance is very low. So what used to happen when we give a direct supply to them, there are the chances that the inrush current is very high, right. For those, what we used to do for the AC motors, we used to give the starting methods. The one of the very common starting methods is by using auto transformers. The third point is the auto transformer is used as variac in laboratory or where the continuous variable overboard ranges are required, right. So these are the advantages. Now coming to our next topic, that was three-phase transformer connections. Now three-phase transformer, we have studied the working, the construction, everything regarding the three-phase transformer, single-phase transformer. Now a three-phase transformer, if you just see, I can be constructing a three-phase transformer as a single unit, or I can be making it from a three single-phase transformers having primary, secondary for the first, primary and secondary for the second, and primary and secondary for the third. This is being called as bank of transformer, right. So if at all I am having three single phase transformers and I need to have a three-phase transformer, so I need to connect these primaries of individual transformers in certain fashion. And we know for a three-phase, either I can connect them in star or in delta. The same is the case with the secondary. I can connect the secondary either in star or in delta. According to that, the windings of the three-phase transformer can be connected in various configurations, as it can be connected in star-star, that means the primary is also connected in star, secondary is also connected in star, or delta-delta, or star-delta, or delta-star, right. Going for the first case, if you just see the figure as it shows, it's a star-star connection. The primary is also connected in star. Star means all the finishing points or the starting points of the three winding needs to be shorted, right. So we have done that. Similarly, on the secondary side also, this A dash, B dash and C dash, those are being connected. So the star-star connection is generally used for the small high voltage transformers. Because of the star connection, the numbers of required turns per phase is reduced. As the phase voltage in star connection, that used to be 1 by √3 times the line voltage, right. Thus the amount of the insulation required is also reduced. So the ratio of the line voltage on the primary side and the secondary side is equal to the transformation ratio of the transformer. Line voltages on both the sides are in phase with each other. This connection can be used only if the connected load is balanced. Now for the delta-delta. Now in this case, the primary and the secondary, both of them are connected in delta, right, forming a loop. We know a delta connection, we have seen that in three-phase connections. So this connection is generally used for large low voltage transformers. Numbers of required turns per phase is relatively greater compared to that of a star-star connection. So the ratio of the line voltage on the primary and the secondary side is equal to the transformation ratio of the transformer. This connection can be used even for unbalanced loading. Another advantage of this type of connection is that Even if one transformer is disabled, then the system can continue to operate in open delta connection but with reduced available capacity. Now star delta, that means the primary is connected in star and the secondary of the three-phase transformer that is connected in delta. So the primary winding in the star connected with ground neutral and the secondary winding is delta connected. This connection is mainly used in step down transformer at substation end of the transmission line, right. The ratio of the secondary to primary line voltage is 1 by √3 times the transformation ratio. So there used to be a 30-degree shift between the primary and the secondary line voltages. The final, that is delta star connection. The primary winding is connected in delta and the secondary winding is connected in star with neutral grounded. Thus it can be used to provide three-phase 4-wire service. This type of connection is mainly used in step-up transformer at the beginning of the transmission line, right. The ratio of the secondary to primary line voltage is, now this time it is √3 times the transformation ratio, right. And once again there used to be a 30-degree shift between the primary and secondary line voltages. Coming to the next topic of ours, that is the classification of magnetic materials. As we have studied a transformer core, and even we will be studying machines, electrical machines, their core would be constructed, let it be stator core or rotor core, those would be constructed with the magnetic material, right. So I need to study the properties of these ferromagnetic materials, what are the kinds of magnetic materials, right. So the magnetic materials are classified into different categories based on their magnetic parameters and also on the basis of the effect of temperature and magnetic field on the magnetic property. So these can be broadly classified into either, I can classify them as diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic or ferrimagnetic, right. Coming with the very first one, that is diamagnetic. So the diamagnetic materials create an induced magnetic field in a direction opposite to an externally applied magnetic field. They are repelled by the applied magnetic field. The permanent dipoles are absent in the diamagnetic materials. If at all I generalize the various properties of a diamagnetic material, so if at all I say the diamagnetic material that experiences a repelling force when brought near the pole of a strong magnet. The magnetic susceptibility of these materials is always negative. The relative permeability is always less than 1. In the absence of external magnetic field, the net magnetic dipole moment over each atom or the molecule of the diamagnetic material is 0. This is due to the pairing of the electrons. The examples, if at all I just give for the diamagnetic materials, those would be likewise bismuth, copper, lead, zinc, etc. Another one is the paramagnetic material, right. What are these materials? They exhibit the magnetism when the external magnetic field is applied. So paramagnetic material loses the magnetism or magnetization in the absence of externally applied magnetic field. So these materials are very weakly attracted towards the magnetic field, right. If at all I generalize the complete properties of the paramagnetic material, then these material experiences a feeble attractive force when brought near the pole of a magnet. These materials also possess some permanent dipole moment which arise due to some unpaired electrons, right. The magnetic susceptibility is very small and it is also positive. If at all I give the examples, then it will be platinum, aluminium, copper, sulfate, etc. Coming to ferromagnetic material, it is of much more concern to us, right. It is the phenomenon in which the material gets magnetized to a very large extent in the presence of the external field. The direction in which the material gets magnetized is same as that of the external field. So if at all I generalize the properties, so these materials, ferromagnetic materials, this experience a very strong attractive force when brought near the poles of a magnet. The permeability is very much higher, greater than 1, right. Then susceptibility, that is positive and high. Example, we are having Fe, Co, Ni, MnAs, etc. Antiferromagnetic material. Now, it is referred to a phenomenon in which the magnetic interaction between any two dipoles align themselves anti-parallel to each other. Since all dipoles are of equal magnitude, the net magnetization is 0. General properties, if at all I say, like ferromagnetic materials, this anti-ferromagnetic materials also possess the dipole moment due to the spin of the electron. The opposite alignment of the adjacent dipoles due to an exchange interaction. The susceptibility is very small but is positive. Ferrimagnetic material. Now in this, the magnetic interaction between any two dipoles align anti-parallel to each other, but since the magnitudes of the dipoles are not equal, the cancellation of the magnetic moments become incomplete, resulting in a net magnetization in the material. If at all I go with the general properties of the ferrimagnetic material, these material possesses the magnetic dipole moment due to the spin of the electron. This material is composed of more state of different transition elements. The susceptibility is very large and is positive. Example, nickel, ferrite, ferrous ferrite. Coming to the last topic of today's lecture, that is the hysteresis loop or BH curve, right? Now, what is this hysteresis loop or BH curve? It can be very much seen on the graph. It is nothing but, as we are saying, it is BH curve. It is nothing but the curve between B, that is magnetic flux density, and H, that is magnetic field intensity, or which we also used to call it as magnetizing force. So the hysteresis loop that shows the relationship between the intensity of magnetization and the magnetizing field. The loop is generated by measuring the magnetic flux coming out of the ferromagnetic substance while changing the external magnetic field. Now, if you just look at the graph, if B is measured for various values of H, right, and if the results are plotted in the graphic form, then the graph, what it can be seen over here, it shows me the BH curve or hysteresis curve, right. The hysteresis in Greek means lagging, right. Which one is lagging? We are just going to discuss. Now, if at all I see the intensity of the magnetism or magnetic flux density B, it is increasing when the magnetic field is increased from 0, right. With this initial curve, if at all I see, when we are increasing this H, increasing H means what? Magnetic field intensity, H is nothing but Ni by L, where this number of turns is constant, the length of the conductor, that is also constant. So the H is directly proportional to just I. That means by varying the current, I may vary the magnetic field intensity or magnetizing force. So by increasing the current, say in the positive direction, right, or moving the magnetic field intensity in the positive direction, it can be seen that the magnetic flux density, which is given by flux upon area, or area is constant, so I must say flux, proportional to flux. So the flux will also increase, the field will also increase, or flux density will also increase linearly, right. It will increase, While increasing the magnetic field, there is an increase in the value of the magnetism also, and finally it reaches the point A, which is called as the saturation point, right, where B becomes constant. This is the point A. While magnetizing or while getting magnetized, right, we can see here the H is increasing. With that, the H is increasing. When the H is increasing, with that B is also increasing. But at the point A, it can be seen after this it is going to remain constant. Even if we are getting an increase in the current or in the magnetic field intensity, this is the saturation. The flux is not going to get increased, or the magnetic field density or the magnetism, it is not going to get increased. So A is the point of saturation. Now, after this, with the decrease in the value of the magnetic field, there is a decrease in the value of the magnetism, right. But at B, when H is equal to 0, the substance or the material that retains some amount of magnetism in it, which we call it as retentivity or residual magnetism. So, if at all I define what is retentivity is, It is the amount of magnetization present when the external magnetic field is removed. This is known as retentivity. It is the material's ability to retain a certain amount of magnetic property while an external magnetizing field is removed. Right? If you just see in the graph, this is the point B, right? At this point it can be seen my H is 0, or I must say the current is 0. There is no magnetic field being applied. Even then we are remaining, or the material is remaining with this much amount of, if this is O, I am remaining with OB amount of magnetic flux density or flux, which we call it as residual magnetism. And the property by the virtue of which the material retains this amount of flux in it, or retains the amount of magnetism in it, even when the external field or the external intermagnetizing force has been made 0, that is being called as retentivity. Moving further, when there is a decrease in the magnetic field towards the negative side, the magnetism also decreases, right? At point C, the substance is completely demagnetized, right? And the force what is required to remove that retentivity of the material, that force is being called as coercive force, that is being given by C. How do I give the definition for a coercivity? That is the property of the material, right? The amount of the reverse, the negative magnetizing force which is required to completely demagnetize the substance, that is known as coercivity of the substance. In this, once again, at point C, once again, here we got the retentivity, the residual magnetism. Further going back, from this point what I have to do? I have to, now to make this residual flux to be 0, to completely demagnetize the material, I need to give this much amount of negative H, or negative force, right? Once again, how can I do that? By the reversal of the supply, or by the reversal of the current direction, right? So with that, I will be having a negative H being applied. With the negative H being applied at point C, we can be seeing that the flux density is becoming 0, the B is becoming 0, right? And the force, how much force you are giving to just to get it 0, that is being called as coercive force. And the property of the material by the virtue of which it makes the residual flux to be 0 at point C, it is being called as coercivity. Moving further, if at all I just continue from here itself, right? Moving further, if the H is further increased in the negative direction, further increase, so it can be seen once again I will be having the magnetization of, because now here the magnet is completely demagnetized, the substance is demagnetized at point C. It will once again continue to get magnetized in the opposite direction. So once again it will get magnetized, and once again I will be having the saturation, but this time in opposite direction, right? Once again I will be having the demagnetization being occurring, right? After reaching saturation point, once again if at all I reduce H, the same way I have increased it. So once again I will be having the reduction in the flux density, once again I will be having a residual magnetism in the opposite direction, and then once again 0. So if at all I complete the cycle of magnetization and demagnetization, I will be getting a leaf-like structure, what it can be seen over here. This complete leaf-like structure, which is given in the blue color, that gives the hysteresis loop or the BH curve for a magnetic material. Now, what are the advantages of having this hysteresis loop, right? So the smaller region of the hysteresis loop is indicative of less loss of hysteresis. Why? Because the area of this hysteresis loss is giving us the energy which is being lost in the magnetization and demagnetization process of that particular material, for which that core is being made, right? So the smaller region or the smaller area of that hysteresis loop shows us that it is giving us a less hysteresis loss, right? Hysteresis loop provides a substance with the importance of retentivity and coercivity. Residual magnetism can be calculated from BH curve, and it is therefore simple to choose the material for electromagnets. I suppose this is all for today. We'll continue in another lectures. Thank you all.